is just to show you several items at each time, and then they will know your preference based on which one you end up clicking. Once they get enough comparison data, they will eventually figure out the personal ranking list for you based on your purchase history and also the ranking results. So statistically speaking, the problem of ranking can be formulated as the famous Bradley-Terry-Lewis model. There are many other ranking models, but today we are going to focus on the BTL model. So at least this is one of the simplest formulation, I think. Imagine we have n players and we want to rank according to their abilities. And in this framework, we are going to model the outcome of a game played between player I and player J by a Bernoulli distribution with probability that is proportional to the exponential of the scale parameter of the player, right? So for example, the probability that player I beats player J is proportional to e to the power of theta I. So we end up with a sigmoid transformation of the difference between the scale parameters of the two players. So ideally, we hope we will have observations from the games between all pairs of players, but this is not realistic. So we consider the possibilities of missing data by the simply sampling scheme. So the sampling scheme we consider in this talk is instead of observing all observations, we only observe a very tiny subset of the comparison results. And this is modeled by an Erdo-Shreni graph. And for each pair I and J, whether they are compared is a random event with probability P. And then as long as Aij equals 1, we are going to observe capital L independent games between player I and player J. So here, I denote the game played between I and J by Yijl, and little l is ranged from 1 to capital L, and the model is specified by the BTL model. Okay. So our hope is to study a random graph that is as sparse as possible. So we wish we can handle a P that is as small as possible, but actually we need to assume that P is at least of log n over n. And for those of you who are familiar with random graph theory, this may sound familiar to you because this is the condition that ensures that the random graph has a single conductive component. Otherwise, with high probability, the random graph will have several disconnected components and the global ranking will be impossible. In the literature of ranking, there are basically two very popular methods. Let me try to review the two methods. So the first method is the maximum likelihood estimator. Let me describe the method in 3 steps. In the first step, we can compute the summary statistic, which is Yij bar. This is the win ratio between player I against player J, right? And then based on this sufficient summary statistic, which is sufficient, you can write down the negative likelihood function. And then the MLE is just the maximizer of this objective function. And finally, you rank the players according to the value of theta I. Okay, so it's a very straightforward method. The second method is slightly more complicated, but I will give you some intuition later to understand the algorithm. This is known as the spectral method, introduced by Negabang, O, and Shah from MIT in 2017. So it is also known as the rank centrality algorithm, which is very popular because it's sort of similar to the PageRank algorithm used by Google in web search. So in this algorithm, you first compute a matrix. Let's call the entry of matrix by Pij. For all the off-diagonal entries, it's defined as the product of Aij and the Yji bar divided by some number d. Okay, and then you specify the diagonal entry to make sure the sum of each column of the matrix is 1. You choose this number d to be sufficiently large such that each entry of Pij is the number between 0 and 1, so it can be interpreted as a probability, right? According to the definition, P can be considered as the transition matrix of a Markov chain. And because it is a Markov chain, you can then find the stationary distribution of this Markov chain by computing the leading eigenvector of the matrix P. Let's call it P pi hat. It's an n-dimensional vector. And then you can rank the players according to the values of this probability vector, right? So the spectral algorithm definitely, yes.
I'm sorry to interrupt, Chow, but there is a question by Obhinandan. So he basically asks in the chat window, you can see your chat also. So often times players of similar skill levels are more prone to be compared. Does this model allow P to depend on theta I and theta j?
It's very interesting. We cannot handle this case for now. The comparison scheme is independent of the player skill similarity. But it will be first of all, it will be a very interesting extension. And later, I will try to argue that the games between players with similar skills are definitely more important in terms of information than games played between players with very different skills. Thank you.
Thanks. Thanks, Obhinandan.
Yeah. Okay. So the spectral algorithm definitely looks a little bit strange. It's not like MLE, right? The meaning is of MLE is very clear, right? The MLE just estimates the skill parameter first, and then rank the players according to the skills. So why is the stationary distribution of some Markov chain related to the skills of players? Well, we can actually compute the conditional expectation of this transition matrix. So this is the conditional expectation, right? And so it has this formula. And then we define a vector called pi. Each entry, pi I, is proportional to e to the power of theta I, right? So after normalization, this is a probability vector. And you can show this pi is actually the stationary distribution with respect to the population version of the Markov chain. So in a sense, the spectral method can be considered as a sample version to estimate the population version of the stationary distribution. And from the definition of pi, you can see that the ranking using theta is equivalent to ranking using pi, right? That's how the spectral algorithm works. And in the literature, the two methods have been well studied, I think, by many people. One of the most important results has been published back in 2019 in Annals of Statistics by Princeton group, led by Yuxin Chen, Chen Jingfan, and their students. So they considered a problem called top K ranking. So in top K ranking, the goal is to select the best K players. It's very much like a variable selection problem. Okay, you just want to select the best K players, and they are able to prove that both spectral method and MLEs are optimal. And let me try to summarize the results. First, I want to specify the assumption that they impose. So here we have the skill parameter. Let me assume, without loss of generality, we actually order the skill parameter from the largest value to the smallest value, right? So theta 1 is the skill of the best player, theta 2 is the second best, so on and so forth. And since the problem is called top K ranking to identify the top K players, it is necessary that we need to, I think my slides get stuck a little bit. Okay. So it is actually necessary to assume there's at least a gap between the ability of the K's player and the K+1 player, right? So we assume there is a separation parameter delta that lower bounds the difference between theta K and theta K+1. And moreover, we also introduce another parameter called kappa. This is called dynamic range of the problem that bounds the largest difference between any two players. In particular, it bounds the difference between the strongest player and the weakest player. Okay, and throughout the talk, we are going to assume that kappa is a constant order. So let me summarize the results of this Annals paper into three different conclusions. The first conclusion says that if the separation parameter squared is greater than log n over NPL, remember, and n is the number of players. P is the probability whether two players gets compared, right? Capital L is the games played between two players if they get compared, right? So up to a constant C1, if delta squared is greater than this ratio, both MLE and spectral algorithm will find the top K set with a high probability without any error, okay? And this is sharp because they also prove a lower bound saying that if delta squared is smaller than this ratio up to another constant, right? So no algorithm is going to work. In a sense, you can understand log n over NPL as the minimax rate of the problem, and both the two algorithms achieve this minimax rate. I would also like to discuss the third result, which is not the theoretical result, but the simulation result, right? So the paper reports a very interesting simulation. They consider an extremely simple setting. This is a two-group setting. So the top K group has a constant scale parameter delta. The remaining of the players has a constant scale parameter 0. And in this scenario, they just do numerical experiments for these methods. And very surprisingly, the error curve of these methods almost overlap, right? So it may suggest maybe it's not just the rates of the two methods are the same. Maybe the leading constants are also the same, right? I will come back to this point actually. Okay, so these are the main results of this paper by Chen et al. Here's our results. We are able to show MLE is indeed optimal, but in a stronger sense. And on the other hand, special method is not. Okay, I will explain why. And moreover, the simulation setting considered in this Chen et al.'s paper is essentially the only setting that you can show special method is optimal. That's why it overlaps the error curve of MLE. So before introducing my results, our results, let me try to define two functions. We call this the variance function. So remember, the parameter kappa is a dynamic range. It bounds the difference between the strongest player and the weakest player, right? So given a kappa, you can solve this optimization problem. This gives you the value of V of kappa, right? So this function is defined in this way. And we also define a second variance function. This is called V bar kappa. The definitions are a little bit complicated, but it doesn't matter. Later, I will show you the plots of the two functions. Okay, so our first result says that if delta square is greater than 2 times the variance function times this ratio of all the log P over N, NPL, then MLE exactly recovers the top case set with high probability. Okay, and you can see that indeed log N over NPL is the optimal rate. But not only that, we are also able to identify the exact constant in front of the rate. The constant is characterized by 2 times the variance function that we defined in the previous slide, right? And if you look at the numerator of this ratio, it's also more precise. The numerator is in the form of the square of root log k plus root log n minus k. So you can see there is a symmetry between k and n minus k, right? This is intuitive because mathematically, the problem of top k ranking and the bottom k ranking, they are equivalent. That's why you see this symmetry. And we also show, we also have a matching lower bound saying that if delta squared is more than 2 times V times this ratio, then no algorithm is going to work. So MLE is not only rate optimal, it achieves this exact constant. Okay, and spectral method requires a different constant, right? Spectral method, the condition for spectral method just replace the previous V by V bar. And we also have a lower bound saying that if this condition does not satisfy, then spectral method will fail. Okay. So now let's try to compare the two different variance functions. First of all, the two functions are increasing in terms of kappa. And moreover, the variance functions of spectral method is always greater than or equal to the variance function of V of kappa, which is the variance function of MLE, meaning that spectral method is always going to be more noisy, right? The only case that they are the same is kappa is 0. So here I show you several plots of the variance functions. The orange is V bar, which is the spectral method. The blue one is the variance for MLE. And I show you the plots for different values of k over n. And the first row are the direct plots. The second row are plots of the functions in logarithmic scale, right? So if you look at the plots in the second row, that you can easily see the functions are not just increasing, they're actually exponentially increasing. And actually, even the difference between the two functions is an exponentially increasing function of kappa. So as kappa grows, the difference is really significant. You can really see a significant gap between the two variance functions. All right, so let me remind you, delta is our separation parameter and the kappa is the dynamic range. And the previous lemma just implies that the two variance functions are equivalent if and only if a kappa is of smaller order. This actually explains why you see this exact equivalence in terms of numerical performance in the two-group model, right? So in this two-group model, by the definition, kappa is delta, right? So basically, since kappa is delta, you push kappa towards delta. So either kappa is little or 1 or delta is very large, right? So by our theory, we just can predict the performance of the spectral method and the MLEs are the same, right? And this is actually essentially the only setting where you can see such a performance. So let's actually try to do some experiments in a more complicated setting. So this is actually a four-group setting, right? So let's consider n equals 200, and the problem is top 50 ranking. So instead of a two-group model, we consider a four-group model. The top 50 people are divided into two subgroups, and the remaining 150 people are also divided into two groups. And the gap between the top 50 and the remaining 150 people is a delta. And as we vary delta, we can clearly see a huge difference between the performance of the two methods. And here's another experiment. We sample the top group from a uniform distribution supported between 6 and 10. And the remaining people are from 0 to 6 minus delta. As we arrange delta, MLE is consistent better, and we can see a gap. Okay. All right. So now I want to explain this role of the dynamic range. As we can see, both variance functions are increasing function of kappa. This just means if you have a larger value of kappa, you get a more diverse group, right? The difference between the strongest and the weakest players gets larger. And this actually makes the ranking problem harder, right? So why is this the case? Initially, it's not easy to understand because we naively thought a more diverse group, then it's easier for us to distinguish different players, but it's actually not the case. Let me try to explain why this should be true by a very simple example. So let's consider we only have 3 people, and we just want to figure out the best place. So K is 1, right? Top 1 ranking problem. So we have player 1, player 2, player 3. Suppose there is no link between 1 and 2, but there are links between 1 and 3 and 2 and 3, right? So in order to compare 1 and 2, it has to go through the comparison between 3, okay? Now we consider 2 scenarios. In the first scenario, the scale parameters are 1, 0, 0. In the second scenario, the scale parameters are 1, 0, negative 1,000. Okay. So my question for the audience is, which scenario is the ranking problem easier? Maybe I'll give you 10 seconds to think. Okay, so it's actually the first scenario is much simpler, right? So right, so from the direct comparison between 1 and 3, since theta 1 is greater than theta 3, theta 1 is 1, theta 3 is 0. Theta 1 is going to win more games in the comparison between 1 and 3, right? And between 2 and 3, player 2 will probably win 50% of the game, right? So if you compare the records against player 3, you can easily conclude that player 1 is the best player. Suppose, say, capital L is about like 20 or 30, you know. But the second scenario, you cannot make such a conclusion, right? Because player 3 is so weak. Suppose you play 20 games, both player 1 and player 2 will win all the games, like 100% win record, right? Then you cannot really distinguish between 1 and 2. This basically explains a large kappa will make the problem harder, at least from the worst case perspective. Okay, so let me quickly summarize the conclusion, and maybe if I still have time, I can talk about a little bit math behind the proof. So first of all, as the Annals paper suggests, both MLE and spectral method are rate optimal. However, we are able to show the constant because the rates are different. MLE has an optimal leading constant. Spectral method has a suboptimal constant. So Bodhi, how many minutes do I still have?
You certainly have 2-3 minutes.
Okay.
2-3 minutes. Yeah.
Okay. Let me quickly do some math. So here's some basic decision theory of ranking. So we can introduce a rank vector called R. This is an n-dimensional vector. So Ri equals J. It means player I is ranked at the J's position, right? And then we can define the top case set to be the set of players whose rank are no greater than K, right? And this is our estimator. Then we can formally define the problem as a decision theory problem by considering the following loss function, which is a Hamming loss normalized by the factor of 1/2k, right? So you can use this Hamming loss is because basically top K ranking is a variable selection problem. So the Hamming loss adds up the type 1 error, which is the first one, and the type 2 error, which is the second term. The reason we have this normalization is because it just by this normalization, the loss is between 0 and 1. It's properly normalized. So we have the property that the loss is 0 if and only if you find the top case set. Okay. So with this loss function, not only you can study the exact recovery problem, you can also study a more general partial recovery problem. And there's in fact a relation between the two problems. If you can find the minimax rate of partial recovery, it immediately implies the condition of exact recovery for exact recovery. Okay. The relation is if the loss is smaller than 1/2k, then it must be 0. The reason is, according to the loss, it's discrete. There's no value between 0 and 1/2k, right? So this relation is obvious. Okay, so here's our minimax rate of the problem. The minimax rate of ranking with respect to the Hamming loss, this is partial recovery, is this exponential rate. And we can explicitly calculate the error exponent. The signal to noise ratio of the problem is determined by NPL delta squared over the variance function. And MLE is able to achieve the minimax rate. So MLE is not only optimal in exact recovery, but also optimal in partial recovery. And special method actually achieves a different rate. The signal to noise ratio is replaced by signal to noise ratio with a bar, right? And the only difference between the two signal to noise ratio is for special method, we have V bar instead of B, okay? And then using this relation, you can directly set up the condition that the minimax rate is smaller than 1/2k, and this leads to the exact recovery condition for the two methods. And the first condition is optimal. The second condition is for spectral method, right? So this is my last slide. Special method is really popular in many different problems, and there are recently some work showing special method are optimal in for example, clustering in the setting of Gaussian mixture model and also in stochastic model. Especially, I want to highlight these two papers. Not only do they show spectral method are rate optimal, but the leading constant of the exact recovery is also optimal. In terms of the error exponent is exactly optimal, right? But in ranking, we actually show spectral method is not optimal. And I think this is really a case-by-case situation. You really need to do careful calculation without assuming the optimality beforehand. Okay, thank you so much, and that's all I have.
Thank you, Chao, for an excellent presentation. Are there any questions? If you have any questions, please write it in the chat window. There is another question, Chao, from Shohom. So I think the question essentially is trying to suggest, what if you have external variables, probably covariates? Can these be used to help in this ranking? And how would you fit it like you can do in logistic regression?
Excellent. This is, again, very interesting question. So for the community detection problem, like if you have a network, you want to do clustering. People have studied the problem called contextual community detection, meaning what if you have extra features, covariates, and this is a similar problem for ranking. We may call it contextual ranking, right? So the general principle is just to maximize the likelihood function. If you can write down the joint likelihood, and I believe that would be optimal. A more challenging problem is how do you define, how do you again propose a good model? That's, I think, in terms of practice, is a more interesting question.
So Chao, if I may ask a few questions on this. So can you talk
Please.
a bit about the computation of the MLE, for example? And in general about the yes. Yeah.
Yes. The computation of MLE is straightforward, especially in the case where we assume kappa is a constant. Because kappa is a constant, the objective function is well conditioned, and it's convex. So you're just using gradient descent, it converges very fast. But when kappa is growing, then it's actually very slow. So we have another paper. We talk about the problem of full ranking. The idea is to use a divide and conquer strategy. You can actually divide players into different leagues, right? And so this sort of gives you a rough order. Then within each league, you compute a local MLE, and because in each league, players have similar abilities, so statistically, this does not lose any information, and computationally, it makes the objective function of MLE well conditioned. So MLE in general is efficient.
So Chao, another follow-up question. So in this talk, you kind of always avoided this scenario where so theta I is I over n, because there all the rankings are coming close to each other, right? Theta I equal to I over n.
Sorry, could you say it again?
So I'm talking about a scenario where theta I is just I over n.
I over n, okay.
Yes, so of course now there is no gap, right? And so what can be done in those situations, and in those situations, which one is a better method?
Oh, theta I is I over n, so then the gap is 1 over n, right? So the gap
right.
between, which means delta squared is 1 over n squared. I think in this situation, because we require, it is required that delta squared should be at least log n over MPL. Yes, okay. So basically, from this condition, you can derive the smallest L to make sure the ranking is possible. So to L should be at least a polynomial order of n.
Okay. So if there are no other questions, then let's thank Chao for an excellent talk again. Thank you, Chao.
Thank you.
Thank you. So now let's move on to our next talk. So our next speaker is Cindy Rush. Cindy completed her PhD in 2016 from Yale and joined Columbia. Now, Cindy also has diverse interests in machine learning, statistical physics, information theory, and high dimensional inference. And today she's going to talk about all or nothing. Okay, now you have taken off the slide. Sorry. She's going to talk about sparse spiked matrix estimation and phase transitions. Thank you, Cindy. The floor is yours.
Sorry, Bodhi. I was making sure that I had my slides working there. But okay, so as Bodhi mentioned, I'm going to talk about all or nothing statistical and computational phase transitions in the sparse spiked matrix estimation. And this is joint work with some collaborators, Jean Barbier at the International Center for Theoretical Physics in Italy, and Nicola Macri at EPFL. So I'll mention this is the first time I'm giving a talk on this work, so it might be a little bit rough around the edges, in which case try to just feel free to interrupt me in the chat, and Bodhi, if I miss it, please just stop me. Okay. So let's see. To get started, all right. Well, now I open the chat. And okay, there we go. Now we're on the motivation slide. All right. So in modern machine learning and high dimensional statistics, one often faces regression, classification, or estimation tasks where the dimension of the feature vector is much larger than the sort of effective underlying dimension of the structure at hand. So some examples I'm thinking of are examples like the MNIST digits, where each digit corresponds to a vector of length 784, but In fact, a lot of work has shown that the effective dimension here is more along the order of tens. Similarly, if you, for the ISO map face database, each of these, face images has a dimension of 4096, but the correct intrinsic dimension is actually only 3 for kind of the vertical pause, the horizontal pause, and then the lighting direction. More generally, natural images, are often sparse in some sort of wavelet basis. So, this low dimensionality is something we see often. So these and other, sorry, there we go. So these and other developments have justified a sort of bet on sparsity principle, which, kind of in a nutshell, says that intrinsic low dimensionality is often a crucial ingredient for interpreting high dimensional statistical models. And so this is what we're going to work on today is based on this principle. So as benchmarks within this context, it's necessary and important to determine both computational limits of estimation, which tell us how much data is necessary and sufficient for computationally efficient algorithms to perform well, and also to establish, sort of our fundamental information theoretic limits of problems, which I'll also call statistical limits throughout the talk, which in contrast to the computational limits provide guarantees for learning procedures that are algorithm independent or algorithm agnostic. So what we aim to do in this work was to establish these sort of fundamental results, the computational and statistical limits, for a specific problem. That's the problem of rank 1 matrix estimation from noisy observations of the entries of the matrix. But in the case where the signal sparsity is actually scaling sublinearly with the problem dimension. So I'll also mention that in this work, we're employing a sort of average case approach in the spirit of the statistical mechanics treatment of high dimensional systems. Where in short, by an average case approach, I just mean that we model the signal using a random ensemble. So in our case, the elements of the signal are drawn IID from a distribution with a vanishing fraction of non-zero components. So why do we do this? Well, in Bayesian settings, when we know the priors and hyperparameters for the distribution of the signal, this approach has been highly successful in allowing us to establish such fundamental limits. And it often yields exact formulas for the mutual information and the minimum mean square error of the problem, allowing one to establish these information theoretic limits. Using this average case approach or this sort of Bayesian approach where we put a prior on the signal has also, allowed us to give exact expressions for statistical and computational message passing phase transitions in the limit of infinite dimensions. And this is what we're going to use to provide these computational limits. So I'll discuss this, what I mean exactly by the statistical and computational limits in a few slides. So I just wanted to talk a little bit about the low rank matrix estimation problem generally. So this is a problem with a lot of applications in image processing, principal component analysis, and machine learning generally, tensor decomposition, and so on. And so because this is a problem that has so many applications, the mathematical analysis of the model is fairly well developed, but specifically in the setting where the fraction of non-zeros in the signal is small but fixed, as the problem dimension grows. And so to the best of our knowledge, this is the only work that addresses the sort of true sparse limit, which just means that the fraction of the non-zeros in the signal is going to 0 with the problem dimension. So in this work, in this talk, I guess, I'm going to show you the information theoretic limits of this problem in this true sparsity setting, as well as the computational limits based on the analysis of an approximate message passing algorithm. So to get started, I'm just going to introduce the sparse spiked Wigner model that we study. Okay, so in the sparse spiked Wigner matrix model, we consider a signal that I'm calling X. So this is a vector that's linked in, and again, we're going to assume that its elements are sampled IID from some sparse distribution that I'm labeling P. So in defining this distribution P, the delta is just the Dirac delta function at 0, and rho is going to be some sequence of weights that changes with the dimension n that will eventually tend to 0. So you know, with this sort of framework, the signal is expected to have a sublinear number of non-zero components, where the number of non-zero components, of course, is determined by this rho. So throughout the work, I'm going to assume that this distribution P is either a Bernoulli or Bernoulli Rademacher. So the signal elements are either going to be 0, 1 or 0 plus minus 1. So then the data that we have in this problem is an n by n symmetric matrix W that has noisy entries. So here I'm defining a parameter lambda that controls the signal strength in the model, and my noise I'm just going to assume is generated by this Gaussian matrix Z that has well, it's symmetric, but the Gaussian elements are IID. So here, you know, we can notice that the matrix W is, you know, a sum of a Gaussian matrix from the Wigner ensemble, that's the Z, perturbed by a rank 1 matrix given by the XX transpose. So this is the spike, right? Is the rank 1 matrix there. So our goal then, right, is to estimate this rank 1 matrix from the data W. Okay, so let's see here. All right, so what we wanted to do in this work was to investigate statistical and computational phase transitions in the regime where the number of non-zeros in the signal is actually decreasing. And in order for this to sort of be an interesting problem, we need that the lambda value, which controls the signal to noise ratio, is then increasing with n. So I just, you know, I'll pause to kind of give you some justification for this, to sort of emphasize that if the number of non-zero elements is approaching 0, then sort of non-trivial estimation is only possible if the signal to noise ratio lambda grows with n. So it's maybe not totally obvious, but here's a quick sort of heuristic justification. It's not too difficult to convince yourself that the total signal to noise ratio per non-zero component of your signal X is going to scale like lambda times rho. So in order to have, you know, enough energy to estimate the non-zero components, if rho is going to 0, you need to have lambda increasing. All right, but before I continue, I'll also take a moment to just define exactly what we mean by phase transition. So, you know, I'm looking for statistical and computational limits in the problem, and what we actually see are statistical and computational phase transitions. So I'm also, I'll go back and forth, sorry, between saying algorithmic and computational, but I mean the same thing there. So, okay, so I'm gonna say that a phase transition occurs if the appropriately normalized, well, I'll say a statistical phase transition occurs if the appropriately normalized minimum mean square error, or MMSE, of the problem jumps from 0 to 1 abruptly with changing problem parameters. And so similarly, we're going to say an algorithmic or computational phase transition occurs if the mean square error of an appropriate approximate message passing algorithm also jumps abruptly from 0 to 1 with changing problem parameters. So in a few more details, so the phase transition, the statistical phase transition manifests itself as a singularity, or more precisely kind of a discontinuous first order derivative in the mutual information between the data and the spike XX transpose. And then this corresponds to a jump discontinuity in the MMSE through relating the mutual information between your data and your signal to the MMSE of the problem through the so-called IMMSE relationship. Essentially, closed form expressions for the asymptotic mutual information allow one to benchmark the fundamental information theoretic limits of estimation. So why do we study approximate message passing in this case? Well, in the spike Wigner model with linear sparsity, so sort of the traditional setting that others have studied, approximate message passing have been shown to provide Bayes optimal signal estimation for some problem settings, asymptotically as the problem size goes to infinity. And AMP is in general a class of polynomial time algorithms that have been applied successfully for signal recovery in a number of low rank matrix estimation problems. And it turns out that sort of based on conjectures from statistical physics, it suggested that the performance of AMP is the best among polynomial time algorithms. So, you know, we're assuming here, which hasn't been proven, but if AMP fails, then any polynomial time algorithm is going to fail. So in this work, to study the algorithmic phase transitions, we're going to study the properties of AMP designed, you know, for the problem we're interested in. And you know, ultimately, what we want to do is provide an understanding of the sort of trade-offs or the gaps between these algorithmic and statistical phase transitions, or the limits of the problem. Okay, so all right. So so what I'd like to do next is just sort of specify the kind of problem regime where these phase transitions occur. So we need to kind of put some more conditions on the rho and the lambda here in order to kind of see interesting aspects of the problem. So one of the aspects of this work is where we identify the correct scaling regimes of the vanishing sparsity and diverging signal strength, in which non-trivial sort of information theoretic and algorithmic phase transitions actually are seen, right? So beyond this, we also determine the gap between the location of the phase transitions, which I'll show you in a few slides. And then we also see that the phase transitions that we witness are the all or nothing type. So it's like, you know, the algorithm works until it absolutely doesn't work. And the same thing with the statistical phase transitions. The problem is, you know, solvable until it's absolutely not solvable any longer. So, okay, so I'm going to just describe in a bit more detail the sort of regime, the sparse regime that I study, and the corresponding thresholds. So the statistical phase transition regime requires that rho, which controls the sparsity of the signal, decreases to 0 more slowly than 1 over n to the beta, where beta is a positive constant that's small enough. And for this, to observe the statistical phase transition, we need lambda, the signal to noise ratio, to grow like negative log rho divided by rho. And so we prove in this regime, a phase transition occurs as a function of this gamma here, which is just some positive constant used to define the lambda. The location of the algorithmic phase transition is slightly different. So here we need rho to decrease to 0 more slowly than log n raised to some power negative alpha, where alpha is just some positive constant, and we need lambda to grow like 1 over rho squared. And so in these regimes, for the Bernoulli and Bernoulli-Rademacher signal distribution, we rigorously prove the existence of all or nothing phase transitions for both the minimum mean square error of the problem itself and the mean square error of AMP. So I'll illustrate these sorts of phase transitions with some plots on the next few slides. So the plots I'm going to show you are all for a Bernoulli signal distribution, but the results for the Bernoulli-Rademacher are quite similar. So here, what I'm plotting on the y-axis is sort of a suitably normalized mutual information. So again, we can relate the mutual information between the spike, which is the XX transpose, and our data W to the MMSE of the problem. So the first step in kind of proving this is to characterize this mutual information. And so what we see is as P decreases, so as rho decreases, where red is the smallest row and blue is the largest, the mutual information actually approaches the sort of broken black line there with an angular point at a critical value, where the critical value is given at the bottom of the slide, and it's just negative log rho over rho. So the idea is that for small rho, the mutual information increases linearly until for small rho, the mutual information increases linearly as the SNR increases up until a certain critical value, and then it kind of flattens out as the SNR increases above the critical value. And so this actually, using this sort of study of the mutual information, we can actually say something about the minimum mean square error of the problem. So the minimum mean square error is basically the best we can hope for. So here, the y-axis in this figure is a suitably normalized MMSE. And what we see is that the MMSE tends to its maximum possible value of 1 when lambda is smaller than the critical value. So the SNR is below the critical value. It develops a jump discontinuity at the critical value, and then takes the value of 0 as the sort of the SNR is beyond that critical value of negative log rho over rho. So this is the phase transition we see for the information theoretic aspects of the problem. So we also observe similar behavior for the mean square error of AMP as a function of lambda. But now the actual critical value has changed. So here the sort of critical value for AMP is no longer negative log rho over rho, but it's 1 over e to the rho squared, where e is some constant that we've approximated numerically. So the figure plots the mean square error towards which our suitably normalized MSE of AMP converges at various sparsity levels. So again, we see an all or nothing transition appearing at the critical value defined by the lambda AMP. And so the transition is kind of occurring as rho is decreasing. So the black row kind of is the giving we're actually witnessing this phase transition effect. So comparing to the figures on the previous slides, Here, the transition has become sharper much faster as rho decreases. And the plot shows basically that for lambda below AMP's critical value, the MSE of the algorithm is always equal to 1. So this is kind of the worst possible. And then when rho is small, there's a phase transition at the critical value, and the phase transition sharpens as rho decreases. So here I just wanted to plot the gap between the two thresholds. So now the horizontal axis is on a log scale, and we see that the statistical to algorithmic gap diverges as rho increases. So in the image, the gap between the two phase transitions is sort of the horizontal distance between the colored dotted lines and the black dashed line. So the gap is the largest, when rho gets small. And indeed, we can characterize this gap by looking at the critical values of the two phase transitions. Right. So basically, the gap is given by well, I should say the following. So when we characterize these critical values, both of our results are established for the regime where rho is decreasing like log n to the negative alpha. And so in this regime, we have the gap defined by the difference between these two critical values. We conjecture that, in fact, the computational result should also hold for sort of the larger regime where rho decreases like into the negative beta. But controlling the AMP iterations is sort of already highly non-trivial. And refining our current analysis to get the stronger result is something we're still sort of working on. But the stronger result is already covered by the information theoretic regime. Okay, so I just wanted to wrap up real quick by discussing in a little bit more details how we actually establish these sorts of results. So I just told you how our work provides new results in the sparse limits along two main lines. So first we give exact statistical thresholds for sharp all or nothing phase transitions at the level of the minimum mean square error of the problem. So we do this by using a rigorous derivation of the mutual information in the form of some variational problem. Next, we established the AMP algorithmic thresholds, and we show an all or nothing transition at the level of the MSE of the AMP. And so this follows from a finite sample analysis of the approximate message passing algorithm that allows us to rigorously track its performance in these sparse regimes. So in a few more details, the information theoretic analysis is done via an adaptive interpolation method that was sort of pioneered by my co-authors, Jean and Nicolas. And it was first introduced in non-sparse matrix estimation problems. So what this method does is it provides closed form expressions for the mutual information between the data W and the signal X in terms of low dimensional variational expressions like that given on the slide. So the adaptive interpolation method could even be extended into this like sublinear sparsity limit is interesting and not obvious. And then from this, we use the IMMSE relation to solve, along with the solution of the variational problem, to find the MMSE of the problem. So, okay. Then I'll just say quickly, to establish the computational limits, we analyze the appropriate AMP algorithm. And this is basically using the state evolution analysis of AMP, which just is a sort of recursion that allows us to exactly characterize its performance. And so when rho is constant, so when the sparsity is constant, the validity of this state evolution analysis follows from standard AMP theory. However, in the sublinear sparsity regime considered here, we have to use finite sample techniques that was first developed in my work with my co-author, Ramji Venkataramanan. And this allows us to find the algorithmic phase transitions. So that's all I wanted to say. The full version of the works on arXiv, and I'll also mention that the context of sublinear sparsity and all or nothing phenomenon has also been studied by some other folks as well. So thanks.
Thank you, Cindy. Thank you for the very nice talk. So I will now pause for a couple of minutes to see if there are any questions. If you have any questions, you can write it in the chat window. So as we are waiting to have some questions, Cindy, if I may ask a question. So here in this talk, you focused on the rank 1 problem, right? What would have happened if you had a rank K, which is larger than 1?
Yeah, so I mean, the short answer is we're not entirely sure, because the rank 1 problem was already pretty hard to analyze, but we think that we'd see, we think it could be extended there. Just, you know, notationally things get a lot more difficult and we haven't tried it, but we think that we'd see the same sorts of phenomenon. So I don't expect that like the regimes where the transitions occurred would change that much, so long as we're still kind of in a low rank setting. You know, you still need, I guess, if the rank is small but fixed, let's say, I would expect that things happen similarly, but I don't think that's kind of just speculation. So
makes sense. Thanks. So let's wait for a few seconds to see if there are any more questions. So Shagnik has a question, and he mentions what happens beyond these regimes of sparsity.
Yeah, so this is another place where I don't totally have a complete picture, but we have some ideas. So, okay, so there's kind of two ways that we could extend the regime, right? So we have our decaying rho. If we kept those the same, but changed the way that the SNR grows, right? So now we have a decaying rho in a specific way that lambda grows, considering that rho. So there, we're pretty sure that that's the right rate that lambda needs to grow. The idea being, if the signal to noise ratio grows too quickly, the problem's easy, and so there's no phase transition, you can just solve it. If the signal to noise ratio doesn't grow quickly enough, then the problem's too hard, you can't solve it. So we're pretty sure here is the correct regime for us to see these sorts of interesting phase transitions. But I'm not quite, it's not clear to me that, well, I think there could be some work done that says, you know, the range of lambda values for which we see the phase transitions. Now we've said, if it grows like this, we do. With the rows, as we mentioned, we kind of believe that the rho decaying like 1/n is sort of the correct rate for interesting things to happen. And so this is where the statistical phase transitions have been proven to occur. for the computational ones, I'm kind of getting a weaker result. And so we conjecture that, you know, if I can figure out a more careful analysis of the AMP algorithm, we should be able to see computational, or we should be able to prove that computational phase transitions occur also if rho is decaying like 1/n. I'll also mention that, you know, we had, you know, the rho's like 1/n to the beta, where beta is less than 1/6 or something for the statistical limits. And we don't think that that's fundamental. We just think it's part of our limitation of our proof methods. And it's not clear to me if you know, beta could be like greater than 1. I don't know actually. So this is still something we're trying to sort out.
Yeah. So I think Shagnik has a follow-up thing. Okay. So he says,
I can answer
why
quickly.
Do you
Sorry. Okay. Yeah. So why is AMP the right algorithm to study? Well, in a lot of cases, it's provably Bayes optimal, meaning that it matches the MMSE of the problem when it succeeds. And then even when it's not provably Bayes optimal, sort of non-rigorous statistical physics methods suggest that it's the best polynomial time algorithm. So there's kind of it's a bold claim, but there is a conjecture there that AMP is going to be the best polynomial time algorithm for this problem and a few others. So many folks believe that if AMP fails, no other algorithm is going to work either. Thanks for the questions. I'll pass it to Weiji.
Yeah, thanks, Cindy. Thanks for a very nice talk. So let's now move on to the final speaker of this session, Weiji Su. So I hope Weiji is here.
Yes,
Okay,
I'm
great.
here.
Yeah, so I just want to introduce Weiji a little bit. So Weiji also graduated in 2016. Now I realize all the 3 speakers have graduated in 2016. Is that correct?
Yeah.
That's an interesting coincidence. So Weiji is in the Wharton Business School at UPenn. He also has diverse interests ranging from high dimension statistics, machine learning, deep learning, privacy preserving data analysis, large scale multiple testing, and so on. So without further ado, Weiji, the floor is yours. Thank you.
Yeah, great. Thank Bodhi for the invitation and for the introduction, and also thank Chao and Cindy for the very interesting talks, and thank everybody for attending. And so I have many friends from Calcutta, and I really hope that someday I can visit the city of joy. So today I will introduce a new privacy definition called Gaussian differential privacy. And as we all know, we are living in the digital world, and so enjoying many benefits given by the big IT companies and many more. And but however, they also somehow know what we are thinking, what we are doing all the time. So our privacy somehow is not as guaranteed as earlier. So then it's arises a very important issue on how to protect privacy. So in 2006, so 4 computer scientists, sincere work, Max Shafi, Nissim, and Adam Smith introduced a privacy definition called differential privacy. So in 4 years later, a paper by Larry Weissman and Shu Henzhou made a connection between differential privacy and hypothesis testing. So this is really a connection between some computer science stuff and something our best friend hypothesis testing. So let me elaborate on this connection. To make this connection, first let's have a setup for differential privacy. So this is a typical example of a data set. So you have many rows. Each row corresponds to an individual, and each column represents a feature. For some feature, it's okay to release the information like gender. I think for most people it's fine to release, right? And age, maybe it's still okay, but salary might be not. For most people, salary is something quite sensitive. And then an example of a mechanism or algorithm in the context of differential privacy takes this form. The question is, what's the average salary of people in this data set, and then what you can report often takes this form: the true average salary plus noise. So noise here is necessary in order to blur your result, to hide some individual information. And now let's define what are the data sets. So two data sets are called neighboring, like S and S prime, if they are almost the same, except for one individual. So here in S, Alice is there, and in S prime, it's Annie. But for the rest of people, like Bob, Charlie, and Dave, they are all the same. So we call them neighboring. And then let's use the language of hypothesis testing. So although now the true data set is S, alternative is S prime. So your job is to make a decision between S and S prime. And on what basis do you make the decision? You based on the output of the algorithm. So you can look at the output of the algorithm and then decide whether it's Alice in the data set or Annie. So intuitively, you see if the hypothesis testing is very difficult, meaning that it's really hard to make both type 1 and type 2 errors small, then privacy is preserved in terms of Alice and Annie. And this is really underlines the essence of differential privacy. So now differential privacy is basically everywhere. So Google and Apple and Microsoft are really using differential privacy in many of their products. So last year, there's the US Census Bureau, and they also use differential privacy in their statistics. So this screenshot is small. This screenshot actually is a screenshot of my iPhone where I was upgrading my iOS, and iPhone asked whether I'm happy to allow Apple to analyze my data, but they say they will use differential privacy. And so I said yes. And 4 years ago, the team of differential privacy was awarded the Goldel Prize in computer science. So now let's talk about what's new in this talk. So far everything is still old. And we introduced a notion called the Gaussian differential privacy. And this is 5 papers where we developed this line of work. And due to time limit, today we only have time to introduce the first paper. So this is based on joint work with Jingshuo Dong, who is a student at Penn, but now moved to Northwestern Chicago for a joint postdoc, and my colleague, Aaron Ross. And so let's make a connection between compare the new notion called F differential privacy. So this is what introduced this talk, and the epsilon delta differential privacy introduced earlier by Cynthia and et al. So first of all, it's the same thing, and they are both interpreting differential privacy by hypothesis testing. So this is the same thing. There's no difference. Now it's the difference. The first difference is we are using the type 1, the type 2 errors, and not only the type 1, type 2 errors, a single pair. We are using their trade-off as our privacy measure. And but in epsilon delta, they use the worst case likelihood ratio. And we are using the function f mapping from 0, 1 to 0, 1 to characterize the type 1, type 2 errors. So this is our parameter. In epsilon delta, since they use epsilon delta, only 2 parameters, 2 numbers to measure the worst case likelihood ratio. So that's the typical way for us to achieve F differential privacy is to add Gaussian noise. And in epsilon delta, usually it's at Laplace noise. So it's a very early preview of FDP. So there are many existing F differential privacy definitions. And so if we look at the 3 criterions, whether the definition is informative, and how do they deal with competition, and how do they perform on the subsampling. And hopefully in this talk, I can convince you that our new F differential privacy is doing well across the 3 criteria. So now let's first introduce F differential privacy. And so we have a trade-off functions. So let's first introduce what are trade-off functions. And since our audience most have statistical background, so it's very easy. So this talk was given to some computer scientists many times, and then I needed to spend lots of time introducing what's type 1, type 2 errors. But here maybe today the life is easier for me. And so here P denotes the output, the distribution of the output of the algorithm, if the reality is S, and the Q is the distribution of the output algorithm, if the reality is S prime, meaning that any is in the data set. Okay, so this is very typical. It's a simple hypothesis testing. We only have one distribution in each of the hypothesis class. So the type 1 error is defined as this. This is the beta is the type 2 error. So given any rejection rule. And now we can define the trade-off function between of P and Q, which is a function mapping 0-1 interval to 0-1 interval. For any alpha between 0 and 1, so alpha is the type 1 error, the value of this trade-off function at alpha is just the best type 2 error. The minimum type 2 error under the constraint that the rejection rule is at level alpha. Okay, so the type 1 error of the rejection rule of phi here is below alpha. So this is the definition of the trade-off function. And the infimum actually can be always achieved. Sometimes you probably need to do randomization, but it always can be achieved due to the Neyman-Pearson lemma. We can just use the likelihood ratio test to achieve the minimum type 2 error given type 1 error constraint. So this is the trade-off function. So given the trade-off function, then now let's define the FDP. So for any algorithm, so here it's necessarily randomized. Then this is called F differential private. If the trade-off function between any two data sets, any neighboring data sets, S and S prime, they are neighboring, meaning that they only differ by one individual. They are very close. Their trade-off function is at least larger than F for any alpha between 0 and 1. So recall that the value of this trade-off function is a type 2 error. So this means that the type 2 error on the left-hand side is always larger than the type 2 error on the right-hand side. So having a large type 2 error means that, okay, the problem is hard, right? The problem is hard. And this means that it's hard to, there's a lower bound on distinguish between Annie and Alice in terms of F. So here the randomization is always comes from the algorithm. So there's slightly difference in differential privacy than in statistics. In differential privacy, we always assume that the data sets S and S prime are given, they're deterministic. So the randomization is necessary from the method M. And here we always, so if F is the trade-off function of P and Q, two probability distributions, then this guarantee is saying that this telling apart Alice and Annie is at least as difficult as telling apart P and Q. So if P and Q are two distributions overlap a lot, then it's really difficult to tell apart Annie and Alice. So their privacy is well preserved. If P and Q are far away, for example, suppose their support do not overlap, then it's very easy to tell apart Alice and Annie, right? So there's no privacy for them. So there is a connection to hypothesis testing. We can also use the region of the hypothesis testing. But here, this definition F is more flexible, especially when it comes to computation. So now let's make connection to epsilon delta dp. So epsilon delta dp is defined as this. Okay, if epsilon the delta, the two parameters are both close to 0, and then these two probabilities will be very close. E is any event. So a result due to Larry Weissman and Schuhunter 10 years ago says that actually epsilon delta dp is a special instance of FDP. But of course, by then there was no definition of FDP. So actually, we adapted their language, their result to our FDP language. So this result says that actually our FDP can be thought of as a generalization of epsilon delta differential privacy. And then what's the trade-off function of epsilon delta dp? The trade-off function looks like this. It's like this. So here, this is the intercept. So intercept. So the length of the intercept is delta, and then you draw a line with slope minus e to epsilon. So here the slope is minus e to the minus epsilon. So the intercept is also here. So everything is symmetric with respect to the 45-degree line. So by the way, this line is basically the indistinguishable line, because here the type 1, type 2 errors sum up to 1, right? So it's just a random coin toss. But if we look carefully, there's something what everybody will be thinking is that why here we have 4 segments, right? 4 segments. So in general, f function, the function f can be any continuous function between 0 and 1. So 4 segments is like having 4 segments is really something of ad hoc, right? Something ad hoc. And moreover, with the probability delta here, we have nothing to say, and any bad event can happen within the epsilon delta definition. So now let's focus our attention to a special case of F differential privacy. So this is the so-called Gaussian differential privacy, the title of this talk. And so Gaussian differential privacy, the F function, is simply the trade-off function between 2 normal distributions, the stand normal and stand normal with mean shift mu. And this trade-off function actually admits a closed form expression. Phi is the CDF of stand normal. And so we define, say, an aggregate set to be mu GDP if the trade-off function is always larger than or equal to this trade-off function between any level between 0 and 1 for any neighboring data sets. So this is a single family parameter family, and this is very related to linear discriminant analysis. For example, you can define this trade-off function for any multivariate normal distributions. As long as their covariance matrix is the same, then the final rejection rule is always a projection, right? You project onto the sun line. So everything can be reduced from multivariate dimensions to single dimension. So that's why we consider a single dimension univariate normal distribution, but this definition can be easily extended to multivariate normal. And due to a statute limit theorem phenomenon you will see later, and so Gaussian differential privacy is perhaps the most important family in this class. And now let's interpret mu. And so here, this is the perfect privacy. Mu is 0. Here, mu is 0. When mu is half, it's here. So you see the both type 1, type 2 error cannot be too small, right? So it's still distant privacy. And if mu is 1, so it's here. So privacy is still okay, I think. But when mu is 3, then privacy is only tiny bit. For example, here the type 1, type 2 error can be both smaller than maybe 10%. And then when mu is 6, you don't see it, because when mu is 6, the trade-off function is just the same as the y and the x-axis. There's no privacy at all. So let's briefly talk about how to achieve privacy in FDP, in Gaussian differential privacy. So the setting as follows, and as a user, you ask a question, theta. So here, according to statistical convention, we need to put a hat, right? Hat, to say that this is statistic. Okay, this is actually statistic, not a parameter. And then the data set will tell you, the curator of the data set will tell you the response, which is just the true statistic plus some certain noise. And how much noise do you add, and what kind of distribution of the noise do you do? So in the Gaussian differential privacy framework, we propose to add Gaussian noise, and how the variance of the Gaussian noise actually relates to the sensitivity of the data set. So sensitivity is just the largest perturbation of this statistic on the neighboring data sets. So S and S prime here are neighboring. Okay, they only differ by one individual. And so this is the largest perturbation. So mu is related to the sensitivity like this. So if the sensitivity is large, we need to add more noise. Sigma needs to be large. Also if mu is large, and means that you are very liberal, and you don't require a high level of privacy, you can also add less noise. So here by this example, you see Gaussian mechanism is somehow like to GDP is just like Laplace noise to epsilon 0 dp. And now let's go to the second part, and the computation and the statute limit theorems. So what's computation? Computation occurs when we have multiple questions about the same data set, and we can ask questions, and based on, you can contrast based on your questions, you can gain more and more about the data set. So the privacy naturally will degrade. So the question every privacy definition is faced with is to understand how composition decrease, how composition compromises under, how privacy compromise on the composition, and how fast it is. So Now let's formally define composition. What's composition? So here we have two compositions, meaning that you have first question M1 and the second algorithm M2. And the M2 here can depend on the output, the response of M1. Okay, you can adapt your question based on what you have seen early on. So this is the composition. Basically, it's just put everything you have seen so far. Okay, M1 in the first component, M2 in the second component. So in general, we can define composition of any number of algorithms. K can be any number. And now let's define the tensor product of two trade-off functions. So we have two trade-off functions, and this is a trade-off function of your first component, and this is the second component. And then the trade-off function of these two trade-off functions, simply the trade-off function between these two product measures. So if the reality is Alice, then your first component will have distribution P, and the second will be P prime. Okay. If the reality is any, and then your first component is distributed according to Q, the second is Q prime. So that's why. So that's the rationale here. So it's well defined, meaning that you can have different choice, but you will still have the same trade-off function. And the operator is cumulative and associative. Yeah, nice algebraic properties. And the last, within the Gaussian differential privacy regime, and the trade-off function, the tensor product is just the L2 null of mu1 to mu k. So so this is kind of an algebra, make composition and algebra. So we have many algorithms, and each is FIDP. And if we consider their composition, and their composition is still FDP, here that the trade-off function is given by the tensor product of all the small trade-off functions, F1 up to Fk. So this can be, in general, cannot be improved in general, and especially when this is a K composition of mu GDP, and then the composition just to multiply mu by a factor of root K. So now let's introduce perhaps the most important theorem in this talk, and this is a central limit theorem for FDP. So the statement of this theorem does not look like a typical central limit theorem. But if you look at the proof, this is just a central limit theorem. But however, I don't have time to talk about the proof today. So now let me introduce the theorem. So just like a typical central limit theorem, we have a triangular array, right? Triangular array, and the length is increasing. The length of K is always increasing. And we assume that if each Fki is very private, in the sense that it's really close to the perfect privacy, which is a diagonal, 45-degree line diagonal. And it's how close it should be. It's basically 1 over root K. And then their composition of all the K small trade-off functions will converge to the Gaussian differential privacy trade-off function for some mu. And the convergence here is uniform between 0 and 1. And the mu, it depends on some statistics of the trade-off functions. Roughly speaking, it's the type 1, the first and the second moments of the trade-off functions. So this is really, derived from the central limit theorem proof. And so this is essentially provides an effective tool for us to approximate competition. So in differential privacy, it has always been a big problem to evaluate, to approximate the competition privacy. So in our FDP, everything comes down to central limit theorem. Everything is reduced to an estimate of a single parameter, which is much easier than before. So this makes Gaussian differential privacy as to FDPs just as Gaussian variables to general random variables due to this central limit theorem phenomenon. So here we can focus on the special case when it's absolute DP. Absolute DP means that the delta part is 0. And then in this case, we have a finite sample version of this central limit theorem. So this is the trade-off function, K-fold composition of the trade-off function, and sandwiched between these two quantities. So you see, if K is large, then it's basically G mu of alpha, right? And you see here, but if we really want to evaluate the exact value of this trade-off function at star alpha, so this is going to be sharp P complete. be complete. So this was given was taught by my collaborators, computer science collaborators. So roughly speaking, should be complete is even more complex than NP complete. So basically, it's impossible to approximate. And but if you look carefully and you see that composition, the approximation error is basically of order 1 over k, right? 1 over k. In contrast to order 1 over root k by the Berry-Eisen bond. So it looks like we are somehow breaking the Berry-Eisen bond for central limit theorem approximation. But this is not. This is really because in order to have the exact type 1 error using the Neyman-Pearson lemma, sometimes you need to do randomization, especially when your statistics is discrete. So this randomization somehow leads to continuity correction in the binomial approximation. So that makes the error from 1 over root k down to 1 over k. So this is an approximation, and the approximation looks like this, and where the exact composition is the red, and but our approximation is the blue. So look, they are very close to each other. So Bodhi, how much minutes do I have left?
Maybe just 2 minutes.
Yeah, good.
Before we, yeah.
Yeah, thank you.
Go ahead.
Yeah. So yeah, the last part is subsampling. Subsampling means that you have large data sets, but only subsample maybe 10% of the data set. So this will guarantee improved privacy. And so yeah, so here this is subsampling theorem. So we only subsample m portion, p portion of the whole data set. And this theorem is saying that the theorem on the subsampling is still FDP, and the trade-off function is given by this formula. And let me go to the result and show you an illustration. So early on, the subsampling theorem before our result is saying that the privacy is this trade-off function. But our subsampling theorem that says that the effective privacy here is given by this red line, the red line. So the improvement is this region. So this is our gain using the new subsampling theorem under FDP definition. So we are done, and hopefully I have convinced some of you that the FDP satisfy the 3 criteria. To wrap up, so there are many things to be done, and for example, especially can we analyze say any benefits using FDP in place of epsilon delta DP for some specific algorithms. Actually, we have done this for deep learning, but I don't. So this really improves the test accuracy using this new definition for deep learning, but we here don't have time for it. So yeah, so this is 3 criteria, and we are doing well. And also, currently the state of art private deep learning is given by FDP. So this is the triangle, and FDP is can reduce to epsilon delta and GDP. Everything here on the central limit theorem, everything goes to GDP. So this is based on these papers, but today we only talk about the first paper. And our implementation of FDP now is available at TensorFlow, their privacy library. So here, everything says that Gaussian now becomes the center of Gaussian of our privacy again. So this is the return of the king. Okay. Okay. Thank you for your attention. So this is all about my talk.
Thank you, Weiji, for a delightful talk. So if you have any questions, please write your questions in the chat window. In the meantime, Weiji, if I may ask again, this is something that I don't know quite well, but if you kind of go back to a picture where you're trying to suggest the problem with the epsilon delta privacy is that it kind of loses at the corners, right? In that, and
I see. So you are referring to this part?
Yes, exactly. So can you elaborate on this? And again, I'm just trying to develop an intuition of what's going on and the improvement you do here.
Oh, yeah. So first of all, absolute delta is a special instance of FDP, meaning that if you use this line as the trade-off function in FDP, then this is equivalent to epsilon delta differential privacy, and everything's same. But broad at a high level, the trade-off function is defined. Actually, can be any continuous convex function between 0, 1 and 0, 1. So there is a priori. There's no reason why we should restrict ourselves to these 4 segments. Yeah. So that's was our motivation when we developed this F differential privacy definition.
I see. So is this somehow related to the fact that suppose I just have IID data from a Gaussian distribution, right? And I want to make that private, right? Quite often in the epsilon delta way of doing it, you would truncate and do things like that. Is that correct? You would need some truncation?
Oh, yeah. Yes, truncation is basically necessary in all privacy definitions. But there's some trick. For example, you can do exponential mechanism. Truncation here is basically necessary, especially when you restrict to additive noise mechanism. Because if you want to add noise, in the worst case, some item of the data set can be extremely large, can be unbounded. So then the sensitivity can be unbounded. So there is the noise can still not hide the individual perturbation. And so I think this is something that we statisticians can make a connection, can make a contribution. Roughly, that is. So currently, the privacy definition is really the worst case. Is a worst case definition, meaning that we want to guarantee privacy for any possible data set. Even Alice and Annie are some aliens. They are very different from our normal people. We still want to guarantee their privacy. And but if we can relax this definition, for example, maybe guarantee some average people's privacy, then this will be much, you can get much privacy definition. Having said this, the crypto community, when I talk to the crypto community, they are not willing to accept this extension because they say the privacy, if some people it's really special, then it's more important to protect privacy for this person. Yeah, but I think, I don't know. I think this is a really complex issue. It's really about the fundamental idea of what is privacy.
Thank you, Weiji. So let's wait for a few seconds to see if there are any more questions. Okay, probably there are no more questions. So this concludes the session. Let's thank all the 3 speakers for 3 excellent talks. Thank you very much. And I will transfer it to Kiran Mona. Thank you. Thank you very much. Thank you.
Thank you.
Are you here, Kiran Mona?
Okay, so maybe Kiran Moy is busy otherwise. So on behalf of the organizers, let me thank the 3 speakers, Cindy, Shao, and Weiji, for a very informative series of talks. And of course, Bodhisattva for arranging this delightful session. And I'm sure our students have benefited a lot from this presentation. And if they have questions in future, would you be able to respond by email?
Definitely, yeah.
Of course.
Yeah, sure.
Thank you so much. And I guess that brings us to today's finishing line. So Bodhisattva, once again, thanks for organizing.
Thank you to the speakers.
With us.
Thank you for taking your time.
Yes,
and thank you, Thank you, Kiran.
Thank you. Thank you very much.
Bye, everybody.
Thank you.
Thank you.
Hope to see all of
Bye.
you sometime in Kolkata, Weiji. I'll try to make sure if I get invited, I'll try to.
Yeah, sure.
I'm really excited.
Try some authentic Indian food.
Weiji, you are most welcome to Kolkata with its sweets and the friends and whatever else you may like.
Of course, with ISI.
Yeah, sure. Thank you.
Yes, so I think we'll definitely have some option in future, but till that time, so since all our speakers and including Bodhida, you are in the United States, so please take care and stay safe.
Yeah.
Guys,
Okay.
take care. Thank
Thank
you.
you.
Thank you all. Thank you. Bye.
Thank you so much.
Everyone, thanks.